Everybody, how you doing? Back for some more science discussion. Hopefully my mic is sounding good. I'll be checking. If there's any issues, be sure to let me know. I'll try to address it as soon as possible. And basically today, as promised, I'll be talking about the sun, about stars in general. And I have the actual masses for at which things happen. Like at this mass, we get a supernova. At this mass, we get a planetary nebula, and so on and so forth. So I'll be talking about those details a bit, the concepts and the principles. I also have several images, so you can see my uh, presentation there, which I'll start momentarily. First, I'll show you my sun pic in the background really fast. And actually, I could just add the full pickup again, actually. Oh, and I'll do that. Seems apropos since we'll be talking about stars. So this is a picture of our sun from August the 3rd, if I remember right. There's some good sunspots on it. And so I think it's a pretty cool pic. I took that one myself with a solar telescope and uh, a digital camera, a Canon. And took months of work to get that picture. See if I could, boom, that makes it a bit more clear. So yeah, took a bunch of work to get that picture. Months of work. Getting the proper equipment, getting the proper extensions to make the camera the proper length from the focus of the telescope, and working with the settings on the camera, but finally I was able to get that pic, which I'm very proud of. It was actually my professor liked it so much that he every the class that I help in, the class that I'm a learning assistant in, at the start of the class, he always has a image in his presentation that's related to the topic or just some kind of science topic or something. So one of the classes, he put my image as the sort of header image for the presentation, and I was able to talk about it a bit to the class and let them know a bit about how I took the picture. And they asked a few questions about the sun and things like that. So it was fun. So awesome. So we'll look some more at that. And let me get the setup back to the way it was. So of course that's my favorite globe picker image. Ah yes. Glad you like it, Lisa. And it will be up in the background through the whole talk. So if I figure I'll try to get some kind of picture or whatever to be the background of the talk while we're going. So today we're talking about stars. So I propose to have my solar image there. And let me know if my volume is okay, by the way, if I'm too loud, too low. I think everything is set up pretty good. I won't be writing on my pad, so I notice a lot when I write on my pad and then have to watch where I put the mic. But since I have a presentation this time, I should be able to just stay at a level of volume and it works out. Awesome. Sounds good. So, presentation, let me start that again. Boom. So, we'll be talking about stellar life cycles. So, since it was already there, I left my little about me slide there a bit. So, that's a bit about me. That's my YouTube, which those who are here already know the YouTube. My Patreon, if anybody wants to support. I have two associate degrees, and right now I'm in my final year of getting my double in astronomy and physics. So I would like to go to graduate school for astronomy, but I know it'll be hard to do that because it's such a small program. But either way it goes, I plan on going to graduate school next year, whether it be for physics or astronomy. Astronomy is my first choice, but I think if I didn't get in for astronomy, I'd rather be in for something. Ironically, one of the professors I work with, she like I help in an EM class, and one of the other professors that teaches an EM class as well, she came to our first like team meeting, and I actually went to a talk she gave, and I didn't realize she actually studied the sun. And I talked to her afterwards. I was like, man, I didn't know you studied the sun, but she was like, no, I don't really study the sun. I study plasma. So she's a physicist. She has her degree, her doctorate is in physics, but she studies plasma, but she applies her plasma physics to the plasma in the sun. So she did this whole thing about the rotation of the sun, and she's studying the rotation of the sun in detail and how the plasma goes. And but she's a physicist, and she, in her mind, she's not doing astronomy or astrophysics. She's doing plasma physics. But in my mind, I'm like, oh, I could do some astronomy even if I don't get an astronomy degree, just depending on how I apply it. I've heard people say that before, like, it's not so much what you get your degree in to a certain extent. I mean, you got to have some kind of physics or something, but as long as you have some strong physics or some strong astrophysics, you could apply it to physics or astrophysics either way, as long as you have the background. So I thought that was pretty interesting. So even if I got into a graduate physics program, technically I can still do astrophysical type research. So we'll see how that goes. Now I wanted to start with I don't know if the proper phrase is coup de grace. I don't know. I don't know what the proper fancy word is, but this is the detail I was missing last time. So I scrolled through the book and read up on everything, and I found this diagram that precisely gave the masses we were talking about. And I won't actually go through all of these in the presentation. I plan on going through sun-like stars, which we know a lot about because we can study the sun right there, as you can see with my images. And also I'll talk about very large stars that go supernova, because supernovas are fun. I have a lot of images. So I have some planetary nebula images, some nova images, some remnants of supernova images, some white dwarf images. So some good eye candy for you all from satellite and other images. So we'll go ahead and get started. So as far as the masses, here's the overview of what we're dealing with. Certainly welcome. Good to see you as always, Lisa. And everybody want to see the chat once in a while. I have it set up today to where I can show the chat like so. So once in a while, when I reply to the chat, I'll have to. I have to. I'm still learning all the software and stuff. So I know like the pros, like MC2, he has it so it scales properly, but I couldn't quite scale the uh, uh, chat size properly amidst my studies and stuff. So, but I got it up there, and I'll show it every once in a while when I read through the chat, so everybody will be able to see what I'm reading. But going through the masses. So if we have a mass that's less than 0.08 solar masses, and you notice that says solar masses whenever you're looking at an astronomy book or an astronomy paper, and it says M or S or anything, aura, and it has a little circle with a dot in it, that's always referring to the sun. So we always, uh, consistently, we phrase everything in terms of what we know. And we're so familiar with the sun, we see how big the sun is. So if I say something is 2 solar masses, well, we know it's twice as big as the sun. So twice as massive. If I say something is 2 solar radii, then we know it's twice as wide as the sun, and so on and so forth. So the smallest amount of mass that we're aware of that can make a star, like when we look through the universe and the galaxy, and we can see the masses of objects by using Newton laws when they're in orbit. So you see 2 stars in orbit, we can calculate their masses, and we know that the smallest mass we've ever found is 0.08 solar masses. So anything lower than that, it doesn't actually form a star. It forms basically like a Jupiter, planet, like a gaseous planet. So that's the lowest one. Now, the lower masses, the most they burn is hydrogen. All they burn is hydrogen. When the hydrogen runs out, they die. But the thing is, they're so small. There's a mass function. I don't want to get too mathematical with it, but it's a function to where we know from observation. We can look at the distribution of stars, and we'll look at that as we go. But we can see how long a star lasts for, depending on how much mass it has. We can look out and we can see stars of certain masses, and we can see when they've stopped burning hydrogen, when they've dimmed, when they've turned into red giants, and so on and so forth. So these stars, these small ones, they live extremely long. And far as we know, all they burn is hydrogen because the mass is not enough to cause enough pressure to burn anything else. When the hydrogen burns out, then it just dies. But of course, we haven't seen them do that yet. 0.8, 0.08 to 0.25, those become helium white dwarfs. So what that means is the star is massive enough to where the pressure, when it starts to make helium, it keeps converting hydrogen to helium, but at a certain point, it can't go anymore, and you end up having basically a core of a star that's made of helium that ends up sitting there, right? That we call a white dwarf. So we'll talk about that when we get to the sun, mostly because the sun ends up being a white dwarf. So if you look at the 0.25 to 8 solar masses, that's referring to the 0.25 to 8 times the mass of the sun. So of course the sun is on the lower end of that, one solar mass. So the sun can get to the point where it may burn some carbon. I actually don't think it's big enough to burn oxygen, but it'll at least burn some carbon. Carbon definitely burn off all of its helium, and it'll get to the point to where the core starts to become built of carbon, and you're left with either a carbon or a carbon oxygen white dwarf, where literally you have this giant, massive object in space that's made of a bunch of carbon, mostly because all of the hydrogen has all been converted into helium. Then a lot of the helium, or most of it, has been converted into carbon, and you end up with, when it burns off everything, it can't burn anymore. You end up with a white dwarf, and we'll talk about and look at some images of how that happens. We'll look at some nebula images. When it's 8 to 12 solar masses, you end up with a neon oxygen white dwarf, which means it starts to burn up the hydrogen, starts to burn up the helium, but the pressure is still so much that it starts to burn helium and convert that, and it's converting carbon and so on and so forth, and it actually starts to fuse neon and oxygen. Right? So when these stars can't fuse anymore, then you're left with this neon or oxygen. Imagine this big giant object that's several solar masses, like bigger than the sun, that's made of neon and oxygen. So that's amazing. And then again, we'll look at some images of these white dwarfs as well. Now, greater than 12 solar masses, that's when they become a supernova, right? When the pressure is so great and the temperature gets so hot that it simply can't contain, the gravity of the material is not enough to contain that force, and it explodes, totally destroying the star. And that's the difference between a nova and a supernova, which we'll discuss as well. I remember when I used to visit this particular Discord server, one of the flat earthers was you know how the flat earthers, they ask questions and they delude themselves and believe that means they disprove something because they're ignorant. And he just kept asking, how does something explode over and over? How does it explode over and over? And I knew the answer, but it didn't seem worth telling him. But I asked him, have you looked it up? Have you tried to see if there's an answer? He kept avoiding the question. And eventually he seemed like, in a resonated way, okay, what's the book? I'll go read the book. And somebody else cut in and said, nah, no, we don't need no astronomy book. And the original guy, didn't mention it anymore, so I ain't mention it either. So I think he really wanted to look it up anyway. He doesn't want to just keep asking the question. But I'll actually talk about novas and what they are and how something can keep exploding over and over again. And so we'll talk about that with the sun, because things like that can happen with pretty much any white dwarf, given the particular size of the white dwarf and the circumstance. So we'll talk about the difference between a nova and a supernova. So again, this is the sun. The sun is a G-type star. Now, if you look at the diagram at the bottom of there, OBAFGKM, what happened is, back in the day, before we even knew about stellar classifications, there was a bunch of women in very good universities. I believe one of them was Harvard, or perhaps the main one was Harvard, and they called them computers. So what they would do is they would be the ones that would uh, 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 look and calculate a bunch of things. You know, they would get the data and do calculations. That's why they call them calculators. We didn't have computers like we have now. And a certain group of them, they studied stars, and they would look at the color of the stars and document the color. And it took a while before we realized what the color meant. So there was a period of time when we thought that the different colors of the star represented different elements in that star. Like literally, like the star is made primarily of this or that element that's emitting primarily in that color range. But eventually we learned that was incorrect. I believe it was Cecilia Payne who figured that one out. But don't quote me on that. I could be wrong about the name. I didn't think I was going to go into history, but I'm just talking about what's coming up. And but she found out that these stars are mostly hydrogen, and the temperature of the star causes certain wavelengths to be more prominent, and that's why we get these different colors, and we put these specters on them. And Lisa says, do your own research means look at other flat Earth videos. That's correct. That's what they do. Is look at a flat Earth video, look at a meme, and then they believe that they did research. You know, the guy that I know who is a flat earther who introduced me to the fact that it wasn't all just a satire, that people really believe this. He used to say that too. Like, I do research. You got to research. You got to go research. And I asked him, well, what do you mean by research? What does that mean? Well, research. He just kept avoiding the question. And finally, it finally came out that he meant he was looking at some YouTube videos, right? And I could tell he was embarrassed by it. At some level of their mind, they know it's just bullshit. They have to, on some level, because just like if you saw me debating with it, and I asked him, okay, you're saying all of this stuff is wrong. You're right. Tell us when the next conjunction of Mercury is going to be, and show us how with your model how you get that. He tried to change the subject. It was like 10 minutes where he would just avoid the question. Then he brought up a link. At some level, he must know that's bullshit. He must know. At some level, but it is wrong with it. It's amazing. At some level, at some point, I just throw my hands up and say, you're just not going to understand these people unless you're in the same level of delusion. But these people didn't do that, though. The computers, they actually studied the stars themselves. And when they looked at certain frequencies, these letters were random. They picked a star that was a blue star, and they said, we're going to call that O. And on down the line, the red stars were called M. And this classification, that's the primary classification, is what it is because that's the stars that we can most prominently see at the time. Now we can see more, and there's more classifications on the right, L, T, and Y. And yes, it never reads reading books or textbooks. So of course, it's all fake, unless they want to try to use Einstein or whatever to quote against himself. Yes, weird. There was even some people arguing in the chat of that debate with satellite data and the CMB. I guess because they heard Witted do it. It's like, did you look up that satellite and realize it's in Earth orbit? What are you doing? It's crazy. Now, looking at this next slide here, we'll talk about the sun in more detail. Now, right now, as we saw in the previous slide, the sun is about halfway through its life cycle. It's about 5 billion years old. We expect it to last about 10 billion years given its mass. And if we look at this diagram, you can see where the sun is in the middle. Oh, let me move this chat. Sorry about that. So if you look at the middle of the diagram, you can see that the sun will be almost directly in the middle of this line. Directly in the middle of the line, the sun is there. And you can see it starting to peel off at the top where it says many red giants. This is just basically what the scientists do is they look at a cluster of stars, they examine each star and simply put it from left to right on the color line, which we know relates to temperature, and they put it up and down on the size line. So if you look at the left, it says 0.01 to 100, that's solar masses. It stops at 100 because that's about the largest stars we see forming is about 100 solar masses. And to the right, you're basically going from the hottest stars to the coolest stars from left to right. The sun is about in the middle. You can see where it says G, yellow, orange, and that's why the sun is peaking at the yellow-orange range, because uh, that's where its peak is at, given its temperature, given its mass. All of these things relate. So when the sun starts to die, it starts to go into the red giant phase. You can see where it's peeling into the red giant on the side, and it starts to increase in size, because what's going on is the inner uh, 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 core of the sun is starting to burn away its hydrogen. So it's mostly helium, and the very, very core of the sun starts to become just a non-burning helium, but it's very hot. And what it does is it starts to burn the hydrogen that's sitting on top of the helium core. So again, in the inside of the sun, that's where it's hottest, because that's where the most pressure is. So that's where the fusion is going on. So the very core of the sun starts to turn to helium first. So you end up building up this gradual, almost like a kidney stone, of helium that's building up in the center of the sun. So the center is not burning anymore. There's not enough pressure there, but it starts to burn the outside, the helium that's resting on the outside of it, and it starts to expand as the temperature fluctuation starts to uh, heat up, because it's basically is a larger area. You can think about it that way. It's a spike in heat, and to use the verbiage the textbook uses, it says they call it hydrogen shell burning. When the central nuclear fires in the interior of the solar mass stars cease, the helium in the star's core is still too cool to fuse, which is what I was saying is helium is not going to burn. With no internal energy source, the helium core is unable to support itself against its own gravity and begins to shrink. At this stage, the star is in hydrogen shell burning. So again, the hydrogen shell burning phase, it starts burning on the outside of the hydrogen on the outside of the helium core, right? So the helium is starting to release heat, is burning the shell. This greatly increases the nuclear reactions. The star becomes brighter and starts to expand. And again, that's why we get into the red giant phase, because that uh, uh, reignition of heat on that outer, larger core, more heat, more pressure, the star expands, and then it peels off the main sequence and starts to be put into the upper right. You see those stars branching out. It's called the red giant branch, and it starts to become large like this. And again, we can see stars where the size is definitely expanded, and you can see how it shows the core in the middle right there. As you can see now, this star is becoming red, so it starts to move to the right side. But at the same time, it's so big, that's why it's so bright, right? So again, looking at the HR diagram, that's why the red giants are up and to the right. They're red, but they're very bright. And by the way, the left, it can be luminosity as well. It correlates because the more so if a star is 100 solar radii, like the stars at the top there, is huge. It has a large region where it's sitting light, so it's very bright. So the bigger a star is, the brighter it is, which means that even though the red giants are very cool, because when they expand, the gases have more room, so they cool down. But they're so big, they still end up being insanely bright. That's why if you look at my solar imagery, any solar imaging, you see those sunspots. To our eyes, those spots look dark. That's why we call them sunspots, because it's surrounded by the brighter areas of the sun that's a bit warmer. But those things are still very bright. But if you imagine a star that's as bright as a sunspot, but 100 times wider than the sun, it'll be a lot brighter than the sun. And we have to calculate that before. So I won't bore you with the calculations now and prepare them, because it's a bunch of math. The concepts are definitely more fun to hear about. Now, what happens is eventually the core starts to collapse, and we're still talking about a sun-like star. It reaches a point to where the helium starts to form into carbon, like we mentioned earlier, and it starts to become a sphere of carbon, which is a heavier element, And eventually what starts to happen, we start to reach a section that's called electron degeneracy pressure, where these more massive elements, helium, carbon, is in the core. The pressure is pushing down on them, and it gets so close that they simply can't get closer together. They can't become more dense because literally the electrons are moving around and not allowing anything to get closer together to each other. So when it gets to that electron degeneracy pressure level, a new energy source begins, and the helium can start to burn because there's so much pressure. And they call that part a helium flash, where because it's burning so brightly, because now it's burning helium, you need a whole lot more energy to burn that helium. There's a whole lot more pressure because things are more massive, and the brightness expands even more, and the star peels out even farther to the right and up on the HR diagram, and we can see this, what is called the horizontal branch right here, where in the middle, I'm looking at the one at the bottom where it says horizontal branch. You can see it's moving from a red giant to the right and moving over to the left, which means that it's still about the same size, even though it got a little bit smaller, but it's becoming hotter. It's moving to the left, which means it's becoming hotter, and the color of it is actually turning more bluish. So it gets really, really interesting. And this is where we end up getting to planetary nebula. So what happens is, you imagine that we have this red giant, this core that's becoming increasingly dense, increasingly hot. At some point, it expands to the point to where the pressure going out overshadows the gravity coming in, and then you get something like this, where the star actually sheds its outer layers and becomes like a large, heavy wind that we call a planetary nebula. Now, it's called planetary nebula, if I remember right from my one of my classes where we talked about the history of it. Back in the day, they couldn't really see what these things were. I mean, they didn't have telescopes like we have now. This one is from the Hubble, so you can see in the subscript. So they couldn't see what these things were, and somewhere or another they mistook them to be some kind of planetary things. It's my understanding, and they called them that. But now we know that they're literally these giant clouds of gas that's spewed out from the core. And if you look, we probably can see the core right there. If you look at the center of this nebula here, in the inside, the core is still there. So the star itself, the core of the star at least, is still in the center. And it's just so hot and so vibrant because it's burning so hotly now with all this pressure and with all the heavy elements, that it's literally just blowing away its outer surfaces. Right. And of course now, because it was burning, it produced hydrogen, it produced helium. It produced helium, it produced carbon. So now this cloud is filled with a bunch of hydrogen, still a lot of hydrogen there, a lot of helium, a lot of carbon. And these things can then become other stars and become planets, which is why we have like carbon and helium and things on Earth, because these things were once stars that died and shed their outer layers. And these things in the future condense again into another star, but now the star starts off with still most of the hydrogen, but some carbon and some helium, right? And if it's big enough, we'll get into how it starts fusing other elements. But all of these are nebulas from sun-like stars. One of the questions that they have, by the way, is why they look so different. So if you look at these, they all look very different, but they all started from from stars that are about the same size, about the same composition. So one idea is that it has to do with the environment that the star is in. You know, each of these stars are in different regions of the galaxy or different regions of the universe. Most of the galaxies, my understanding, these are stars in different parts of the Milky Way. So, but depending on the environment that's there, uh, you know, perhaps certain gases get more excited and so on and so forth, or perhaps there's more things in between us and them. Or they think it might be something in the process that we have to still learn. So that's still an open question, by the way, exactly why they look so different from each other. But that's a solar mass sun. Any questions came up, Lisa, or anybody else? We move on to the next topic of larger suns, and we'll spin the larger suns, larger stars, and we'll spend the second half talking about what happens with things that become novas and supernovas. I'll give a second to see if any questions come up. So, well, that sounds good. So I'll keep it rocking. And if anything comes up, let me know. And so we'll talk about some larger stars here. Now, we looked at this before. We're going to focus on the, and actually one more thing. Let's talk about let's talk a bit about the white dwarfs. That's what I meant to talk about a little bit. Thanks, Lisa. So, and she was saying a good presentation, which I appreciate. And she was saying that I answer the questions a little bit before they come up. So that's always a good thing. So now we talked earlier about in the center of the nebula, the star is still there, the core is still there. So what happens to it? It's literally just a white dwarf that's sitting there. So if you look at Sirius B, that's a white dwarf. It still has a companion. And ironically, Sirius A, its companion star, could have gotten as big as it is from absorbing some of the stuff that Sirius B shed when it got to its last phase. We'll talk about that. Now, this, what I thought was interesting, is actually a field of white dwarfs. So to read the caption, it says the globular cluster M4, seen here in figure 1813, as seen through a large ground-based telescope at Kitt Peak National Observatory in Arizona, is the closest globular cluster to us at 2,200 parsecs away. That's the picture on the left. On the right, this view of M4's core, so we're literally zooming in on the core, by the Hubble Space Telescope, shows nearly 100 white dwarfs within a region of less than 1 parsec across. So literally, each of these things are the cores of stars that have shed their outer layers and planetary nebulas. But of course, you imagine that there's a whole bunch of these things close together. They're all radiating a bunch of heat and radiation, so they all pushing stuff away. And eventually, this clears out all the gas, and you're just left with a bunch of white dwarfs. So literally, this is just a field. It's almost like a cemetery, I guess you can say. It's like just a field of the bodies of dead stars, basically. Just the cores of stars that's died. And basically what's going to happen is these things are just going to, over millions of years, just continue to cool down. They're technically not burning. It's just large chunks of helium and carbon and oxygen that's just so heavy that it's compacted very close together. It can't be compressed anymore, so it's extremely dense. It makes it extremely hot because it's so close. But still, over time, they're cooling down because we can see they're radiating energy. So after so long, they'll end up becoming a black dwarf, where literally it cools off so much that it's just not radiating heat anymore. If you're familiar with this, yes, my understanding is that's a cluster in our galaxy. Yes, in the Milky Way galaxy. And because I really don't believe we will be able to zoom in this closely if it was a different galaxy. Now this is something like maybe Andromeda, but that's still far away. Like I don't really think we can zoom in this far on things in other galaxies. Because we see, when I say we, like in class, we see galaxy pictures a lot, and they're always like, it takes spectrum of the galaxy as a whole. Like when they study galaxies, they take spectrum of a galaxy as a whole. But we know the percentage of stars that form of certain sizes. They call it the initial mass function. So, for instance, if you have a big nebula, like all of these stars, for instance, they push the nebula out somewhere, and let's say the nebula in one region, it starts to condense and make another cluster of stars. What we know is going to make few big stars and a whole bunch of small stars, and there's a continuum along that, right? And we're pretty there's still some uncertainty about the smaller stars because they're so small we can't get a good view of them. With the bigger stars, we're pretty good with the initial mass function. We're starting to fine tune the smaller ones because JWST can see smaller, lighter stuff, so we may get that more fine tuned. But let's say if a cluster makes 10 stars, it'll make like two giants and like uh, uh, three, sun-like stars and like five very, very small stars, for instance. So what we do is we look at the structure of the galaxy, we see how much light is coming from it, we get the wattage of its energy, and we could do calculations and say, okay, that galaxy must have somewhere around this distribution of stars, but we generally can't see the individual stars in the galaxy. Yeah. But that might change soon. And that's just what I'm seeing. Like maybe there's some more advanced stuff that they're doing that didn't get to yet. But so far, from what I'm seeing, when it's a galaxy far, far away, we just look at it as a whole. But we may get there. And again, there's may be some data I didn't get to yet. But I always thought this was pretty interesting. Now, this is another interesting thing about these white dwarfs, by the way. We're going to talk about novas. If you look at the image on the bottom left, well, I guess technically the middle left, that's actually a nova. And if we look at the right, that's what's happening. So let's say a star like the sun that dies, and let's say it has a companion, just like how we saw earlier, right? Companions are pretty common. So we saw how Sirius A and Sirius B, it has a companion, right? So it's common for for stars to have companions. So what happens is you have this core that's very hot. It's made of carbon, it's made of helium, it's made of oxygen, whatever type of core it is just sitting there. It's close enough to a companion star where it can draw mass from the companion star, and it starts to build up a layer of hydrogen and helium or whatever is drawing from the other star. But the layer, it doesn't quite hit the star. It like comes towards the star, and this angular momentum causes it to orbit, right? But it still starts to fall slowly in. Just like how if you look at the movie Interstellar, there's the accretion disk around the black hole, and it's slowly falling in and getting hotter. That's why there's that ring around the black hole, like that really happens. So it happens with stars as well. Things orbit around them, it starts to fall in. As it starts to fall in, it gets warmer and warmer. And what happens is when the layer gets hot enough, it ignites. So if you imagine if you have like your grill, if you have a grill and you put some lighter fluid in the grill, and you light the lighter fluid, well, it shoots up in a bright flame. But when the lighter fluid burns off, well, your grill is still there. Your grill is not going to burn because it's made of metal. But it's the same thing that happens with the stars. Like you have this very dense hydrogen, helium, carbon, oxygen core. It's so dense, it's a solid. And the gas that's swirling around it that eventually settles close to it and ignites, it burns up, but the star itself doesn't. And that's how we can see it go nova, not supernova, but nova. And if you look at the image on the left side, you can see how the igniting gases on the surface are expanding because it's igniting, but you can see the core still in the center there. So the core that's still there will eventually draw some more matter, and it could explode again if the companion is still there feeding it stuff. So that's a nova. And that's different from a supernova, which we'll get into a bit later, but I thought that was pretty cool. And that's a simple answer of that flat earther, by the way. You can find that in any basic astronomy textbook. You can see images of it, satellite photos. We see novas. We know what's going on. But again, they just believe in a delusion. They've convinced themselves that somehow being ignorant means that they know more. So they just keep asking the question over and over, don't actually look to find out. But this is going on with that. And there's an image to show one of them. And we can see them pretty regularly. I don't remember the exact number, but so many of them happen every year. I mean, it's not really a big deal. Because companion stars are so common in the universe that it happens kind of often. Yes, this says all pictures are CGI. That's why I keep my planet picture. By the way, I notice every time I'm like doing a debate or something, or I'm doing a talk on MC2's channel or whatever, somebody asks me about my Earth photo. Why don't you have a real photo of Earth? It might be fake. I don't know. But it was a real photo from Earth. They'll say it's fake anyway. So it shows how dishonest they are. They're like, why don't you have a real picture? Well, if I had a picture of him around 8, you would say it was fake anyway. So you're just a liar. And what does it matter anyway? Well, because the Earth is a globe, I can't have a cartoon picture if I want one. I mean, it's just ignorance and delusion. It's crazy. I'm gonna keep that picture, by the way, so I can continue to make fun of them when they say, "Why don't you have a real picture?" Like, what would I do if you really had one? Well, would you say it's fake anyway? And why does it matter? So I'll keep using that picture because I think it's fun. Now, red giant. Now I'm bringing this a bit farther to look at a sort of fuller progression of the stars. So what I'm going to do is I'm going to go from the top left down. Like this is the progression of a cluster. So if we're looking at a cluster, it starts with the top left image where there's a bunch of young stars. In the second image, you can see how some of them are starting to peel off at the top. There's stars that's starting to die. In the bottom image on the left, you see more starting to peel off. The main sequence is becoming shorter. If you look at the image at the top on the right, you can see we have a lot of red dwarfs now. Now it's starting to get to the point where the sun is about to die. If we look at the bottom, we see that there's a lot of progression in this constellation of stars. Most of them are starting to die. The only ones that are still alive are the ones at the bottom that are so small, they're burning so coolly that they're going to last probably another 14 billion years, about as long as the universe or whatever. And but the ones at the top right, those are the giants that we're about to talk about now. At the top right, where it says the asymptotic giant branch, those are the ones that are so massive that they're going to explode, right? So what happens is they're so massive, the pressure is so big, to where with the white dwarfs, like how the sun will be, the pressure is not enough to start burning, for instance, carbon, so it just becomes a carbon white dwarf, where it's not heavy enough to burn helium. If it's smaller, like it was only, a half a solar mass or whatever, and it just becomes a helium core. These large stars, they're so heavy, they have so much pressure, they start fusing all of these things, right? Hydrogen goes to helium, helium starts fusing to carbon, carbon starts fusing to oxygen, neon, magnesium. And the interesting thing is, by the way, if you were to look at a diagram of these elements, you can see how the fusion rate is always sort of a double, because it's almost like it's fusing two hydrogen to helium. Then it like fuses two helium to carbon, which is why it doubles up. I don't remember the exact numbers, but if you look at a periodic table, and then look at these elements on that table, you can see why the fusion happens in this order, because it's just the way the combining of these elements, the way the elements double up, the amount of protons there makes these elements. So it all adds up with what we know about elements, and then what we can see as far as the elements and the trace elements that we can pick up depending on the temperature of the sun, of the star that we're looking at. Now, the thing is, again, these things are so massive that the pressure is so high that they burn a whole lot faster. And that's why you might be able to jump to a particular slide. Let me see. Yeah, I think I can. So that's why if you look at this first image, I put some of the lifetimes there, like the carbon oxygen size suns, about 100 million years to 10 billion years. But look at 8 to 12. They only last 20 million years, only 20 million years. Because they're so big, the pressure is so great, they burn everything a whole lot faster, so they die a whole lot quicker. And that's why, again, looking at the HR diagram, that's why the stars peel away from the top, because they're so hot and so big that they start to die first. Which is why we can put these stars on the HR diagram and see where the peel is, and then we know how old how long ago that constellation of stars was formed, because we can see, okay, the star died at that point. We know a star at that point that becomes a white dwarf that's this bright, that's this color. We know it has this much mass. We can calculate the pressure. We can calculate how fast everything was burning, and we know how old that whole system is, because we know how old that star is, and that's one of the last stars to die, right? So we know the life of something that's just died. We know the life of everything that's the same age of that thing. You see, so that's how we know how old that grouping of stars is. So let me know if that doesn't make sense. So for instance, here when we see these large massive stars, what happens is when they die, the pressure is still so great that it does actually explode. So let me see if I can use some of the verbiage that they use. It says astronomers classify supernovae in two broad categories, type 1 and type 2. These classes differ by the light curves and composition, right? And this, by the way, is, remember, I'll read the caption before I go past this one, a supernova called SN 1987A. And you can see the supernova is actually in the right corner up there. So if you look at the corner, there's an arrow pointing to the supernova. At the moment the photograph on the right was taken, the photograph on the left is a normal appearance of the star field. So we're good enough at this to where we can actually predict when one should happen by looking at the nature of things when we examine these constellations. And again, we could put things in the HR diagram. We know how old the thing is. We know when things should be dying, of course, according to the age of the constellation. So we can actually point our telescopes there and capture a picture when the thing explodes. And Lisa says, I thought some of the JWST images of the oldest galaxies show star formation happening earlier, sooner than previously thought. Maybe I'm misunderstanding. You know what? I asked my professor about that. He's very good at this stuff. We look at some of his papers in class, so he's very published and very cited. And I asked him about that, and he said, 'cause I saw something online where it was some kind of how they try to be all fanciful. I hate when they do that, but it was something like JWST disproves the universe. I don't know what it said. And it says something about how JWST is seeing stars beyond the edge of the observable universe, or older than we thought the universe is, or whatever. And I asked him about that. And he said that's not really possible because the observable universe literally means that the light would take so long to come to us. So anything older than a certain age, the light wouldn't have enough time to reach us anyway, right? So for instance, something that's 15 billion years ago, we'd have to look 15 billion years into the distance to see that star. But if we look 15 billion years distant, the light wouldn't have enough time to reach us because we don't see anything that's 15 billion years old. So I would have to look at it. I saw what you're talking about, but I didn't look at it in detail. It just seems like they were just being sort of like when they did that thing where they were like, the Earth is the moon is in the Earth's atmosphere. And they tried to, and of course the flat earthers ran with that. But really what they meant was it's like one hydrogen atom per billion cubic meters or whatever that's floated that far out. Is, so I'm sure it's something like that. Yeah, it just the thing about it is this, like, scientists publish things at certain levels in certain fields. So the cutting edge of science, you're only going to know if you're actually doing it, right? Like the people who are actually doing research, they literally, have the telescope studying these things, and they're looking and seeing it happening, and they know what's going on because they're literally doing it, right? So that's original research, and we can get original data and we can study it, but that's the original raw data from what we studied. We know that supernovas happen like this because this is the data. We can look at the spectrum, we can see the size, we can see the mass, and so on and so forth. The next step is going to be scientific papers. So that's when they take what they did with their raw data, they write up scientific papers, but these things are complicated. It's got all the math. I have to read them as part of my studies, and it's complicated. They don't even tell us to read the whole thing. They're like, don't even try to read the whole thing. They like just read, to us at our level. But they're like, look, all you have to do is when they like this, let's say they assign us a paper to read. They say, oh, look, all you have to do is read the introduction, the conclusion, look at the figures. Like they just point out a few things they want us to know because it's very hard stuff, and most of the stuff we can't understand it anyway. We read it, right? But that's directly saying what's going on. And then you have textbooks. Textbooks are basically what's really going on, but it's watered down to the level of that, undergraduate, graduate. Just like now I'm relearning some things that I did earlier in my college career, but it's more in depth. Like instead of getting a magnetic field in one direction, now I have to get a magnetic field in three directions, like the actual three-dimensional magnetic field, not pretending it's only going in one direction, for instance. Um, but that's still like college graduate school. But then when you read something like on the website you pull up online, it's even more watered down. So that stuff you have to really take with a grain of salt because they like I'm saying, just trying to be fanciful to get clicks, or they speaking in a way that leaves off a lot of details and it's easy to misunderstand it ironically because they leaving so much stuff out. So my professor was like, I don't know what that is, and he actually he literally, his team literally used JWST. Like they literally get data from JWST, so he would know. He would know. If anybody would know, he would know. Because he's literally using the telescope and he showed us some of the images and data he got. And he's doing stuff like this. He's looking in the far universe and trying to learn this stuff. And his graduate student, she's doing some stuff on the smaller mass stars. She told us about that the other day. So these people are really doing that stuff. And I asked them, and they're like, yeah, that don't seem like so. It sounds to me like it's something fanciful, you know. But yeah, I mean, it's over my head too. Look, I mean, it's hard stuff. But again, like it's just the nature of it is and that's why these people focus on so many things because there's so much stuff to learn that you can only really learn it sufficiently if you do one thing. So like my professor, he researches this and that's what he does, and he has this specialty, and people have their specialties, and they write these papers that's focused on that specialty. But generally, when you read something that's like general public stuff, just be careful because it's like watered down to the point where it's easily misunderstood. So that's that. Now, this was a actual supernova that we saw, and this is the two types. So I'll keep this image up while I talk about the two types, and I'll read what it says word for word. It says, these classes differ by their light curves and their composition. Type 1 or I supernova are hydrogen poor and have a light curve similar in shape to that of a nova, right? So if we look at the type 1, what's going on is it's still a binary system, a white dwarf. And but what happens is these things, they're big enough to where when it draws on the matter from the neighboring star, it's a limit called the Chandra star limit. I never really read that word enough to know to pronounce it correctly. But if it has enough mass, the heat and pressure is enough where it doesn't just burn the outside, it actually ignites the star itself, like the core itself ignites. That's how much pressure it is because it has so much mass. And that's why it takes larger stars to become supernova because it has to have enough pressure to make enough heat to actually ignite that core. So when that whole core ignites, you can see how if you look at the image on the top right, there's literally nothing there anymore. So when we look at the nova, picture of the nova, you can see that there's still something in the center there, right? And of course, these things are so bright that we can't really see what's in the middle anyway, technically. But we know that these things are so bright and so intense, and we can examine the spectra that's coming from them, and we know that the whole thing is exploding, right? And we call that a type IA. And the interesting thing is these happen at a certain particular mass to where they're so uh, consistent that we can actually use them to measure distances because we know when we see a type 1A supernova, we know how bright it is because they always have to be about this certain mass when they ignite. So it's going to be a certain mass, it's going to be a certain size. So like earlier, a certain size is going to be a certain luminosity. So we know how bright that thing is, but we can see how dim it looks to us. And there's a simple calculation to see how far away that thing is. So that's how we can, for instance, find out how far away this nebula is that exploded, because we can literally look at the supernova right there and we know is a type, we know what type of supernova it is. This one doesn't mention particular, but if we know what type of supernova it is, then we can actually see how far it is pretty easily. The type 2 supernova are hydrogen rich and have characteristic plateaus in the light curve a few months after maximum. The type 2 supernova is a core collapse supernova. So basically what's happening is these things are so heavy that the core itself is not necessarily starting by something building up on the outside. These things are literally so massive that the whole thing collapses. and then burns up that way and explodes. So type 1 occurs with a carbon-oxygen white dwarf in a binary system. This type is called a carbon detonation supernova, the type 2. So literally the core of this thing actually explodes. And again, it has to be big enough to where we talked about the electron degeneracy pressure. It has to literally be enough mass to overcome that. And if it's not big enough, it's not going to happen. And of course, we're not going to talk about this now, but stars could eventually get so big, so massive that when they collapse, they can't even expand again. And then we have a black hole. Well, those are like extremely large. So you're talking about, since we know stars are about 100 solar mass at the largest, usually going to be up there like 50, 70, 100 solar masses. They're going to be in the becoming black dwarfs because it's so massive that even when they collapse, it's too much gravity to light can't even escape those things. So of course, a hydrogen molecule is not going to escape. So it just stays compressed and becomes a black hole. So basically what's happening is, in those senses, is it overcomes electron degeneracy pressure. Then you end up with a neutron star. Like, it can pack so much that the electrons and protons combine to become neutrons. And you have a neutron star. But then when it gets even bigger, it collapses past a neutron star and becomes a black hole. Ah, yes, I know who you talk about. I like her. She's cool. Yeah, yeah. I looked at looked at her channel before. One of my professors at UT, she specializes in black hole. Her name is Shoemaker, Dr. Shoemaker, and she does black holes a lot. I was in her class before, but I was taking a waves class, but I realized I didn't take the prerequisite for the class, so I dropped it. But I did notice she was going to incorporate some of that into the class. It would have been an interesting class to take. I do have one more semester. Maybe I could still fit in another class with her. But here's, by the way, a remnant of a supernova. This is my last slide, which is a supernova happened. And let me read the uh, citation, the notation here. It says the remnant of an ancient type 2 supernova. This is a core collapse supernova. It's called the Crab Nebula. It resides about 2,000 parsecs from Earth and has an angular diameter, excuse me, of about 1/5 that of the full moon. So this thing is literally only 1/5 the size of the full moon. Is how far away it is from us. But you imagine this thing was so big and so heavy that the core collapsed and exploded. That's how massive it was. The Hubble image shows the nebula's complex filamentary structure. The bluish glow that permeates the nebula, especially visible in the insert, comes from high-speed electrons moving in the intense magnetic field near the nebula's core. You know what? I can't say I know her first name. We're going to take a look real fast. Should take a moment. Let's see. You know what? It just came to me. It's Deidre. Deidre or Diane. But let me just check to be sure. I believe it's Deidre, or yeah, it's Deidre. It's Deidre Shoemaker. If she's related to her, I don't know, but it's not her though. But I could share her what you call it? What you call them? Whatever you call it. What? Profile? Let me share a profile page real fast. And boom. Uh, boom. So that she is right there. So Dr. Deidre Shoemaker is a physics professor, gravitational physics. Gravitation. That's why I actually focus on black holes, because gravitation. Yep, it's starting to come back to me. Gravitational wave detectors. So if you see two black holes collide, that's a good instance to see gravitational waves. So she's studying things like collisions of black holes, collisions of neutron stars. We talk about neutron stars are so heavy that the electrons or protons collapse to become just like a thing of neutrons. So all the helium, all the hydrogen, all the carbon, all of that stuff goes away, and it becomes neutrons. And these things collide and cause gravitational waves. Usually I get Darryl Strawberry, like the baseball player. Once in a while, I get chuckberry too, but usually I get Darryl strawberry, one of the famous berries. But awesome. That's all I had today. So I want to make good on the promise. Talk about the details of the masses of stars and which ones go supernova and which ones, so on and so forth. So as we can say, there's a whole lot of categories. I know there's a lot more to do within an hour, but I picked two. The one we know well, Sun, and the Type Ia supernova, which I know pretty well. Talk a little bit about the ones that go black hole and neutron star. But there you go. Some masses, some what happens with the masses. Hope you enjoy it. So I don't have a topic set for next week. So give me some suggestions. I may even do something that I'm doing in class next week because I have some tests this week. So I probably won't be on with tests this week, but I do have a EM exam. I was talking about doing the three-dimensional stuff. I have that exam the week after next, I believe. So maybe I'll do some EM stuff next week, since I'll be studying a lot of that stuff for the exam. So that's probably what I'll do. So next week I'll probably do something with EM. It'll probably be a little bit of math. So you should be ready for a little bit of math next week. Maybe I'll do that. You're certainly welcome, Lisa. Lisa says, I appreciate your presentation. It's very informative. I'm glad you like it. And oh well, I enjoy doing this too. And yeah, I could focus on the test and do this at the same time. So that's probably what I'll do. I'll do some EM stuff. That's right. That's what they say. That's one reason why I do it. They say the best way to learn is to teach. And oh yeah, and I missed that line. Still awesome name to have. Yes, Earth's pretty cool. So awesome, y'all. Good seeing y'all. I'll see y'all next time. I'll be back next week, same time. I'll prepare for some electromagnetism stuff, some 3D electromagnetism stuff. I'll see what I'll do. I'll try not to make it too math heavy. But I'm pretty sure I'll try to do some kind of math or something. We'll talk about EM. Hey, y'all, have a good evening.